So it will be the good, the bad, and the ugly today. And seeing as this is a 132 kilowatt solar array, the most powerful source of energy on the island, do you feel lucky? Mixing my metaphors there, that's dirty Harry. But anyway, so today I'm going to be discussing the island and energy on the island, and where it's coming from, where it's going, what we can do about it now and in the future to make, come on, don't do that, whoops, to make life a little better here. Anyways, so here, that was our solar array. You should go out and look at it. This is our average total energy usage by month in kilowatt hours, average 2015 to 2018, and the blue line is our usage, and the orangish line is our production. And you can see that in January, March, April, which are all summarized as one, that it's basically duplicate, because even though it's not producing very much in January, March, April, it is outproducing what is being used on the island, because there's like one person on the island, and likewise October, November, December. Actually, it's probably, the orange line should probably be above the, you know, if theoretically it would be above those other lines during that time. But that's a general pattern for solar production, is that on a yearly basis, it's a bell curve. It's going to be, you know, I showed you that yesterday with the curves of the input into a window, you know, the heat coming in a window. Same thing, bell curve high in July, August. And for that matter, on a day-to-day basis, the production of a solar array is a bell curve, starting at 0 first thing in the morning, going up to a maximum in the middle of the day, and then going back down to 0 at the end of the day. Now, of course, the problem being that human beings don't use energy in that way. We don't all, you know, slowly ramp up and turn more and more things on as it approaches noon, and then, you know, start turning things off. Our usage has a number of humps and bumps and drop-offs in it throughout the day, although you can generally assume that, you know, from, you know, midnight to 6 a.m. there's not going to be a huge amount of usage. But we do have a spike, you know, sort of at you know, supper time, when, you know, or just before, or just after, when the kitchen's going here, and in fact, here's a breakdown of where electricity goes in this place. Now, this is slightly out of date, because you notice that wastewater treatment at the bottom is almost 30%, it's like 28%. But as of the past few weeks, we have a new wastewater treatment system here that is probably going to use a lot less. So that might very well go below the kitchen in terms of electrical usage. Now, you can see that the cottages and units, you know, even the RO water maker and all that, it's all pretty small, you know, in comparison to the kitchen and the wastewater treatment. That's where most of the electricity is going. The kitchen is a combination. Apparently, I've talked to both Alex and Kristen, who are in charge of that, not in charge of that, but, you know, in terms of the environmental people on the island. And a lot of where the power goes in the kitchen is refrigeration, freezers, refrigerators, and that's pretty true for any household. Just to like lay it out to your household as well, that the refrigerator is that thing that is sitting there on 24/7, 365. I mean, it cycles on and off throughout the day, but you never turn off your refrigerator. So you might have some things like a microwave that'll suddenly, pull 2,000 watts, but it's on for 3 minutes and then it's off, right? But the refrigerator is just faithfully there all the time. In the kitchen, it's refrigeration and there's dishwashing. So there's one load that's sort of going along all day. It might be a bit higher during the day because it's warmer during the day and it's going to be cycling harder during the day. And then the washing machines, the dishwashers, are going to be spiking right after each meal, right? Which is fine at lunch because, hey, there's the sun, middle of the day. Not so great down on the shoulders of the curve. The wastewater treatment, that's pretty complex because you have some parts of it that are humming along, processing much of the time. Others where they're periodically doing like a great deal of pumping at one time, where there's wastewater accumulating at two different points and then being pumped into the main station over there several times a day. So there's possibilities of adjustment there. But you can see that really when it comes down to it, the kitchen and the wastewater treatment, even if we reduce that demand some, that's where we can really get some effects. And beyond that, the hotel, the underworld, the RO water maker, those kind of things are opportunities, but not as big opportunities. So I looked also at fuel use, like absolute direct fuel use, and I made an estimate. I went to the Confrey list and where everybody comes from, and I went to Google Maps and calculated some travel distances and used some pretty average figures for maybe a little bit above average figures for gas mileage. And I knew that some people weren't, probably going to be flying from like long distances and used pretty standard numbers for, the effective gas mileage of a person in an airplane. And so in graphical form, here we have it. You can see that the electric generators that make electricity for them, they are the main thing. But then if you look at Confrey Travel and Leighton Ferry, the Thomas Leighton Ferry, if you add those two together, that's the big usage. Most of the energy usage involved in Star Island occurs before you set foot on the island and after you leave. That's most of it right there. And the Leighton Ferry is the slightly bigger of those two. I mean, I like big boats and I cannot lie, but still, the Leighton Ferry is, in fact, aside from the electric generators, that's huge. And the charter boats, if you add in the charter boats, that's where the fuel lies, right there. Cooking and heating is down the scale a ways. So, we need to work on the electrical generation end of things. But we have to, a lot of it is just us and our own lives. Now, what we could do about the Leighton Ferry, I don't know, because I assume that the folks who run the ferry have done about all the optimization that they can. I mean, they're getting paid by the trip, and they're paying by the hour for both fuel and personnel. And so they have an equation to do. They could actually save fuel money by going a little bit slower, but then they would be paying more in personnel money, right? So there's that equation. But, yeah, in the back?
Do you have a breakdown as to how much of the latent fuel consumption is from hauling the concrete or by hauling the water?
I have no idea, no clue on that one. No clue on that one. A lot of it has less to do with actual mass and more to do with speed. I'll let you in on one of those great, things that people, one of those things that people don't know, is that the amount of effort it takes to push a vehicle through a fluid, whether it's a car through the air or a boat through the water, it's drag, and drag goes up by the cube of the speed. So if you double the speed, the drag, the force you need to push it through the water goes up by 8. Right? So very small adjustments in speed result in a great deal of change in the amount of energy it takes to go through the water. And a boat hull has an optimum speed. It has a design speed. And if you go at that design speed, it's very efficient. If you go even a slight bit above that design speed, the efficiency drops off dramatically. So you have to find the design speed for your hull and go there. The latent is a displacement hull. That is, it's not planing up on the water like a bass boat. It is going through. It is displacing the water, and so it has a very specific hull speed. And I'm sure that the latent crew, the people who run the ferry, have done all the numbers on that. So we're still, you can see that the wood pellet heating, it's practically nothing, and the groundskeeping pumps and diesel vehicles, that's nothing. Cooking and heating, yeah, certain amount there, but there's not too much you can do about that. So I don't know, maybe we have to have a conversation with the ferry company and the charter boats and see, if there's anything they can do about optimizing their energy use more. I'm doubtful. But yes, you can optimize your travel by putting more people in a vehicle, by not speeding.
Moving closer.
Yeah, well, yeah. There is a saying. There is a saying that the most efficient vehicle in the world is a moving van. Right? Because if you end up closer to work and recreation and shopping, that's going to save way more money than you buying a super efficient car. Yes, the con-free travel is a big deal. Just as an aside, because I just love telling people this because it blows people's minds. But if I could wave a magic wand, say, and America stopped speeding on the highway, right? America drove 65 in the 65, 55 in the 55, 50 in the 50. Russia's economy would collapse. And Putin would probably be overthrown. Because we use 25% of the world's oil, roughly speaking. We're 5% of the world's population. We use 25% of the world's oil. If we stopped speeding, I've looked into this. It would cut our energy use by about 7 to 10%. So it would cut world energy use by somewhere, 1.7 to 2.5%. Now, you remember a few years ago, OPEC was struggling to get 0.5% of world oil production off the market to bring the price of oil back up. 2.5% would be a huge glut. There is really no storage in the oil system. Oil is pumped out of the ground, it's put into tankers, it's taken places, it's processed, and it goes into your gas tank or wherever your oil tank. And even though there's huge tank farms at Cushing, Oklahoma, and places like that to store that, literally the U.S. strategic oil reserve will last a time measured in days, right? It's not like we have years of oil stored. So, you know, the relationship between production and consumption is fairly finely balanced. So if we created a 2.5% glut in the oil supply in the world, the price of oil would probably drop to about $25 a barrel from its present, you know, 65 or whatever on the international market. And that would cut Russia's GDP by about a third, and their government income by about a third, and their exports by about a third. It would completely crash their economy. A lot of Persian Gulf nations would, you know, also suffer. You know, the 2,000 princes of Saudi Arabia would have to use gold-plated stuff instead of solid gold stuff. But you know, it would really hammer the oil exporting economies in a big way. And that's just from us not speeding. Literally, it's that finely balanced. And I'll get into the whole policy implications a little more later, but I just wanted to lay that one on you, that not speeding is one of the best things you can do. When you actually go from going 65 to going 70, it's like paying an extra about 12 to 15 cents a gallon for gasoline equivalent, because your gas mileage like drops so much, you know, for each little increase. So here's pounds of CO2 adjusted for fuel type. And, you know, of course, wood pellet heat, it's wood, so not really much there. Although I will note to you that if your wood pellets travel more than 600 miles to get to you, you're burning oil, right? It's like there's enough oil being spent moving the wood, a 40-pound bag of wood pellets, that it's essentially, you know, net. You're on the advantage. So, electric generator is still up there. Okay, let's talk about shading. You can see that those solar panels right there, which are our solar panels, they're made up of a whole bunch of little cells, little squares. So you can think of each one of those as a pump, like a little electric pump. And they're all, you can see the little stripes going along them. Right? You can see the little stripes going back and forth along them. Those are effectively the wires that connect them. So they're connected in series, like Christmas lights. You know, old-fashioned Christmas lights where one goes out and the whole string goes out. You know, those young people don't, but you know, we those of us with gray hair remember those. Well, that's exactly what those are like. So if you shade one cell, as you see right there, even if it's only 5% of the total area of the module, you can lose 50% of the module, like 50% of the output of the module, because it's generally sort of 2 strings per module. If you lose that module, those modules are strung together as well to build up the voltage. You have a higher voltage, so you lose half of that entire string of modules. So you can lose a couple thousand watts of power because you've shaded one cell of one module. All right? So keeping brush and bits of leaves and things like that off of your modules are incredibly important. And then, of course, there's the observation deck, which is put right up close, you'll notice, and you're shading, we're probably losing 100% of that module and 100% of that string. So we're losing about 2,200 watts from that little bit of shading right there. And it's shading all the way along. So 2,200, 4,400, 6,600, you know, you're losing a chunk of the 132 kilowatt array because of the observation platform. My first and primary recommendation is that the observation platform should be moved back from the array at least 4 feet. You want to think of an angle of about that from the lowest corner of the module so that the morning sun can actually come in and start hitting it. So that's my first recommendation. Now, this is kind of a complicated diagram, but I just want you to look at the words in the upper right: sensitive loads, adjustable loads, sheddable loads. I don't know whether sheddable is spelled that way, but okay. Sheddable, fine. Optional loads, whatever. Sensitive loads are like the fire alarm system, right? You cannot turn that off. Forget it. The refrigeration. Refrigeration we'll put that in adjustable. But sensitive loads are life safety loads, a computer network, something like that, can't just turn on and off. Adjustable loads, of course, just like the name, you can use them a little more, you can use them a little less. And then sheddable loads are loads that are done periodically and are less time sensitive, like laundry. You can do it right now, you can do it an hour from now, as long as it's ready tomorrow, fine. So there's different categories of loads. Also, sometimes you see down there, you see an electric car down in there. Electric cars, vehicles spend a lot of time sitting. So if you have an electric vehicle, you can opportunity charge that. You can charge it now and not charge it later, or wait, or whatever. So that's a load that if you're in the middle of charging and it's like, oh no, we have a power shortage, you can shut that off for the moment, and it's fine. So let me just draw some stuff here. I'll just project. So here we have power, and here we have time during the day. And here's your solar production curve, right? It's peaking in the middle of the day, solar noon. And the problem is, of course, that our human activities, right, there's a certain amount of what we might call base load, things that are operating no matter what, 24 hours a day here on the island. That's always going to be there. And then above that, when everybody gets up and starts using water and using lights and using, this, that, and the other, we'll get a spike, and then it might drop off a little bit, and then we'll have another spike, at lunchtime with the washing machines, the dishwasher's going, and it might drop off, another one at dinner, and then it drops off, to the base load again. So there can be multiple load spikes during the day, and the pattern of those spikes and the height of those spikes can change from day to day. It could be different on a weekend than on a weekday. If there's certain particular activities, if there's certain schedules to maintenance, laundry, things like that. And in this daily schedule, we have a certain number of spikes for the sewage treatment, which is the big load here. Even if we reduce it some, that several times a day, there's going to be pumping episodes where pumps use a lot of electricity. And so you'll have a spike here and a spike here and a spike here. So one of the things I've talked about with Kristen Simard, who's the sort of environmental coordinator here, is looking into the possibility. And I'm just spitballing here because I'm going to have to talk to someone about the actual functionality, the details of the functionality of the sewage system, the possibility of compressing those pumping sessions in a little bit to get them in at least on the shoulders of the solar production. I mean, they're going to have happen every day, but another concept is that you've got this base load that's going 24 hours a day, and a lot of that is refrigeration, right? The refrigerators and the walk-in freezers are going all the time. So how do we deal with that we've got this, and this can, depending on the cloudiness and this and that and the other, can, like, you could have, if you had a cloudy morning, like this side of the curve can sort of cave in a bit. Actually, it is right now because of the shading of the observation panel. I went out and looked at the computer and the output from the thing, and you look at the output of the solar, and this side of the curve is caved in a bit because of that morning shading. But it could be caved in the afternoon by a cloudy afternoon or something like that. And it's like, well, what do you do when you've got this constant base load of refrigeration and this is going all over the place? Well, remember how last night my teaser was, how do you store electricity using ice cream? Well, I don't know the exact set points on the freezer system here, but let's say it was 10 degrees Fahrenheit. That's the temperature of the ice cream and the frozen broccoli and whatever else is in the freezer. And let's say it's the middle of the day and you have a dip in usage and you have excess solar. Well, right now, if you have excess solar, the charge controllers, the devices that meter out the power into the batteries and see how full the batteries are, let's say the batteries are full. At that point, the charge controllers throttle back and cut off somewhat the modules, the actual generation from the battery, so that there's potential electricity that's going nowhere, right? You've throttled back on the modules. Well, at that point, you could change the set point of the freezers from 10 to 0, let's say. So you could chill the ice cream down an extra 10 degrees. Now the ice cream doesn't care that it's 10 degrees colder. It's going to be just a little more solid. It's going to take a hotter spoon to get it out of the thing. But 10 degrees, no big deal. Even 15, it's the broccoli doesn't care. But then later in the afternoon, when you're down in the shoulder and you start underproducing, you can put the temperature setting back up to 10 where it was. And you can turn off the freezer for a short period of time. And it will go back up to 10 and you're not demanding electricity. You've stored electricity in the ice cream, effectively. And then you've delayed the point at which you turn on the generators. And you can do that with all sorts of things, not just the ice cream. There are a lot of ways to store energy in the final product, right? So, the question in the back, sorry.
That is in fact what we do with the reverse osmosis system. Because of the way the batteries are sized versus the size of the array, we found in the middle of the day that we had excess capacity just as you described.
Right.
And while we have water delivery on the lake and recovery from the cisterns, we had this RO system sitting here. We had this free electricity that was otherwise going to be throttled back.
Yeah.
The average engineer manager realized we can make water with it. And store
Right.
electricity.
Yes. Kristen told me that you were actually, and I think Alex also told me that you were doing that. Yeah. And that's great. That is exactly what you should be doing, trying to match that demand curve with the supply curve. And there's all sorts of things. Pumping water, if you're heating anything, if you're compressing air, if you're refrigerating things, a polyethylene tank, a 500-gallon polyethylene tank is the cheapest energy storage you can buy, right? It needs virtually no maintenance. It'll last decades, and if you keep it out of the sun. And compared to the cost of batteries to provide the electricity to fill that tank, the tank is like practically zero cost. One of the things that we might want to consider doing on the island is actually, even though we have people manually turning on the RO at particular times and saying, we've got excess energy, is actually going to an automation system that changes set points. There are systems out there for what's called a microgrid. This is a microgrid. We are our own utility that looks at how much sunlight is coming in, looks at the output of the solar, looks at also data from the past about what the average use curve is over time. So we can predict, like, there will probably be an uptick in the usage curve, you know, here and here and here on these particular times of day, these particular times of year. Look at the state of the capacity of water tanks, the capacity of sewage tanks, and so on. The temperature of refrigerators and freezers, and coordinate all this to prioritize sensitive loads, of course, they're on all the time, but prioritize adjustable loads over sheddable loads, where you could say, okay, I'm going to put a load of laundry in this washing machine and hit the on button, but it's not going to turn on right now. It's going to wait until there's some excess solar, and then it will turn on and run. Likewise, any kind of battery charging, you know, outside the main battery bank, but even sometimes the main battery bank. If the main battery bank is at 95% state of charge, it's almost fully charged, you might say, you know what? There's this other usage that we have to do now, right? Like the morning's sewage pumping. We got to do that. The sewage tank is full, so we're going to leave the batteries at 95%. We're not going to bring them all the way up, and we're going to prioritize that, which has to happen. We'll do that with the solar power, and then later we'll bring the batteries from 95 to 100. So you can have a system that is looking at all that, and even perhaps looking at online weather data and scraping predictive weather data for tomorrow, the next day, and saying, well, it's going to be cloudy tomorrow, so we're going to adjust our expectations and our priorities for that. Or it's going to be a blue sky clear day all day tomorrow, so we're going to adjust our priorities for that. And so you can actually, without somebody sitting there pushing buttons, have a system where it's trying to get that production and that usage curve matching as much as possible so you can get the maximum electrons out of it. Another concept is, well, there are a lot of people charging cell phones and laptops and tablets and things like that. Many drops make a bucket. And it may be an idea to, it is an idea, maybe a good idea, I don't know yet, to create a sheddable charging station so that you can put your phones, your laptops and all that and plug them into certain outlets that are going to be on or off depending on the solar input, so that, you know, if you're like, yeah, I'm going to put my phone and charge it and I'll come back and look at it this afternoon, you know, whether it charges in the first 3 hours or the next 3 hours or the last 3 hours, it doesn't matter to you as long as it's somewhat charged when you come back. So the outlets, the dedicated outlets for charging would be turned on and off depending on our solar availability. And that would be another little bit. It's about point shading, you know, you a percentage point here, a percentage point there. Like Senator Dirksen, $1 million here, $1 million there. You're talking about real money. Or maybe it was $1 billion, I don't know. So there's all sorts of usages like that that we can adjust to minimize our use of generator power. That's the general idea of saying, like, how can we store energy in the final product, and how can we shed loads at night and in the shoulder times of the solar. But aside from that, there's the question of actually reducing the overall base load. Now, you all seen wall cubes, right? Those little black or white or whatever cubes with the plug in them that you plug into the wall, and there's a skinny little wire that goes to your electronics, right? There's the brick that charges your laptop, right? That is like a heater. These are all little transformers, right? They transform 120 volt AC power down to 5 volt or something like that, or 12 volt to charge your thing. They have a primary coil and a secondary coil, and even if they're not charging, even if you're not plugged into your computer, your phone, or whatever, they're using about a third of the energy that they would when they were actually charging. So if you have a 100-watt brick for your laptop and you leave it plugged in, it's using about 30 watts. So let's see here. 30 watts times 24 hours, that's 720 watt hours. That's almost a kilowatt hour. Times 365 is 262 kilowatt hours. So 262 kilowatt hours, your average household uses about, 20, 25 kilowatt hours a day. Divided by 25. That's like 10 days of electricity. If you leave your laptop brick plugged in all the time, you're getting 365 days of electricity a year, and you're paying for 375 days, effectively, right? I tested, when my house was off-grid, I tested my range, my stove, my kitchen stove, and it has the little clock in the back that's on all the time. That's 14 watts. That's like leaving a light bulb, a compact fluorescent light bulb, on 24 hours a day, and it's like 5 days of electricity a year, right? And when I was off-grid, that really mattered, So I've got it on a switched outlet. I turn my clock on my stove never says the right time, except randomly. I turn it on, and then I use my stove, and then I turn it off. But the point being that that's the smallest load in the house, that's really tiny, and yet it's using 5 days of electricity a year. And so you wonder, you look around the place, you wonder, like, how many things are sitting there sucking up 14 watts, 20 watts, 18 watts, something like that. Here's another one of your, amazing factoids, that if America unplugged all its wall cubes and coffee makers with a little clock and stoves with a little clock and DVD players and cable boxes and all that kind of stuff that's sitting there idling all the time, it would be enough electricity to power a medium-sized Eastern European country. Like Romania could run on our wasted electricity from wall cubes. It would be like taking 3 medium-sized American states offline. Just wall cubes and idling electronics. It's become more and more as time's gone on, and it's a huge demand now. So
on the other hand, they don't use transformers nowadays. They use electronics instead, and they're getting much more efficient in that regard.
yeah. But
switching power supplies.
But still, there are a lot of things out there that are sucking 10, 20, 30 watts continuously. Still, you can get them. There's a thing called, one of the brands is called a kilowatt meter, and it's a little thing that you plug into the wall, and then you plug your appliance into it, and you let it sit for a few days, and it will tell you how much electricity it's used over those few days, and you divide by the hours, and you're like, oh, okay, I'm using X kilowatt hours a day to just keep this thing sitting here. So yeah, they're getting better about it, but power strips are your friend. And I'm wondering, looking around the island, how many things are there that are sitting there idling that don't have to idle? Yeah.
It was up Oceanic 3 to have the whole lights on.
Yeah.
Incandescent bulbs.
Really?
Yeah, a couple. I found at least one.
All right. Well, there's something. But, you know, you put in motion sensor lights in places, and, you know, I've been actually, the retirement place where my parents are, you walk down the hallway, it's like a science fiction thing, you walk down the hallway, the lights come on as you walk down the hallway, and it's you know, it saves a lot of.
A very cheap watt meter is your hand, because I noticed most of my wall cubes are cold. However, the Verizon box is quite warm.
Right,
That's
yeah,
the
there we
watt
go,
meter.
yeah. You're,
After
it's the digital one, the digital watt meter, right there.
more than a couple of watts, it's a warm.
Yeah.
And the power company will sell these power strips that sense when there's no demand and
Right.
they're shut off. So those
Yeah.
are potential
Yeah.
savings there.
So there's a combination of things we can do here, including patrolling the place effectively for incandescent light bulbs, wall cubes, things like that. Maybe get some of these light strips. It'd be interesting to do an audit of the island and see, like, well, where is all this going? There are places that will do sub-metering. Vendors can come and do sub-metering, so you can actually tell, like, is there something here that is using power that we don't know that it's using power? There's people I know who've gone in and done this sub-metering in industrial plants, and they're like, oh my God, that compressor is cycling twice as fast as any of the other compressors. It must have a leak. But they didn't know that. It was just like, yeah, all compressors cycle. But this one was cycling much faster, and so they found the leak and fixed it, and the energy demand from that particular compressor dropped in half, right? So there's these things that you don't notice because they're just sort of in the background until you actually quantify them. So there are ways to sub-meter various parts of your electrical system and figure out, like, where is this electricity going? Until you know where the electricity is going, you don't know where you're wasting it. So there's an audit to find out where it's going. There's the possibility of doing controls to better match the electrical provision and use. And then there's just behavioral stuff, like, you know, for the moment, like plug your phone in the middle of the day, and, you know, things like that. And, you know, there's that possibility of you know, storing, you know, putting more RO water storage capacity in so that we can, you know, really focus that on the middle of the day. Or putting, I don't know, maybe putting more sewage storage capacity in, I don't know. Then there, of course, there's the question of, can we put in more production capacity? That's the last thing I would do. Conservation and efficiency is always less costly than production. Always, 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 always. But when you get into an island situation, as we are, whenever there's a rule in the remote power business that whenever you carry diesel fuel across salt water, solar is always cheaper. Right? It's just, you know, it's one of those things where, you know, you buy diesel fuel, you know, at the pump on the mainland, you know, for $3 a gallon or whatever, but by the time you get it out to the island and you have the fuel cost to take it and the cost of the boat to take it and the handling cost of people, paying people hourly to handle it and monitor it and maintaining your sort of, you know, it's $6-9 a gallon or something like that. It's you know, it's somebody once figured out that this was years ago. The Department of Defense, the U.S. Department of Defense, was buying diesel fuel for $1 a gallon, like super bulk, you know, by $1 a gallon. But by the time it was poured into the gas tank of an armored vehicle in Afghanistan, it cost $72 a gallon. Because, you know, you had to ship it and ship it again and ship it again, and then you had to have a bunch of guys with weapons protect the tanker as it drove out. You know, you had armored vehicles using fuel, following it along as it went out and protecting it and all that. So the final cost was absurd. We're not quite there, but still, diesel fuel is far more costly out here. So you know, we really need to look at the externalities of fuel use out here. You know, the cost of fuel aside from just like the raw pump price per gallon, and do the math against the cost of an increased size of a photovoltaic array, or increased battery storage or something like that. Again, batteries are incredibly expensive. Batteries are like pet rabbits. They're delicate, right? They need feeding every day. They need, they need a nice environment, comfortable environment. And they break your heart and die anyways after a few years. You know, it's just like there's no winning with a pet bunny, or you know, they're great, you know, while you have them, but they're expensive and they die. And so anything we can do to lighten the load on the batteries is a huge deal. And anything we can do to avoid getting more batteries. The one advantage bunnies have is that they create more of themselves than batteries. You've got to fork out the money. So there's that. Actually, here's another little aside that I could sell you a kilowatt hour of electricity for $120. And you'd think it was a screaming deal. I could sell you a AAA battery at half price. The AAA battery has so little energy in it, but it, it costs $1 or something like that. And if I sold it to you for 50 cents, it would be like about when you buy a AAA battery, you're paying about $240 a kilowatt hour for that. But it's portable, it's convenient, so you pay that. But it's one of those little battery guys and even the batteries in your system here, which are much less expensive, you're paying probably 30 or 40 cents a kilowatt hour, maybe more, to put the electricity in and pull it out again. Because of the limited lifespan of the batteries, every time electricity goes in and out, it's killing them a little bit. They're getting closer to death. So your cost per kilowatt hour involves the lifetime cost of the batteries, what it costs to replace the batteries, as well as the maintenance and all that. So a kilowatt hour that goes into the battery and comes back out has this premium of 30, 40, 50 cents tacked onto it. So anything we can do to adjust production to consumption and not have that electricity go in and out of the batteries is a win. You have a question?
I'm curious about the rechargeable AAAs and AA's. It keeps the battery out of landfill, but I'm not sure if there's any efficiency in those
It's not so much of an efficiency thing because charging and discharging all that, but it is one rechargeable battery is equivalent of a 55-gallon drum of non-rechargeable batteries. Like 55-gallon drum, fill it up with like Duracell batteries, or one AA rechargeable. Take your choice. So rechargeables, always rechargeables, and a loop. Good species of these, ENELOOP, Eneloop. They keep their charge for a long time. Get the real ones, not the knockoffs. So, anywho, that's about what I got for you folks. Ready to take questions? And then you.
So you talked about storage. It sounds like mechanical storage makes a lot more sense. So you mentioned refrigeration, maybe there's some medium that's better than ice cream.
Well, it's what we've got, it's what's in there, you know.
Pumping water, and then having it generate electricity in off-peak times. It sounds like that might be a better system than these chemical batteries.
Yeah, the problem with pump storage is that you need huge volumes of water and very large drop. So it would take a mountain that we don't have on Star Island to really make pump storage work. But in terms of pump storage, as in we need to pump water anyways, we already have pumps. So we're going to pump the water when we have the electricity and not when we don't. When we have the solar, not when we don't. That's a way to store where you don't have to invest anything more in equipment. You've already got the equipment. You're just using it at the right time. And the thing about using the ice cream and the broccoli and whatever else is in there is that you've already got the refrigerator, you've already got the freezer, you've already got the frozen food in there. You don't have to spend any more money. All you have to do is change the set point. You know, it takes some money for the control system to change the set point, but you don't have to buy any new large hardware to do it. So you're using what you've already got. You're just using it more intelligently. So in the back, and then you, and then.
How helpful would it be to find other generation capabilities, such as possibly wind, that work at different hills? So we don't have, the building up shoulder times.
Yeah, there's such thing as tidal. He was talking about other generation possibilities. There is tidal power and there's wave power and things like that, but they're all extremely immature technologies. They're all pretty much one-off, custom, experimental stuff. And there's some interesting things coming down the road with wave power generation, but yeah, it's all custom and expensive and experimental when you need somebody, you know, who knows what they're doing to mess with it. Wind, no. Wind, but people just have like remarkable objections to that. But if you look across the bay there at Appledore Island, you will notice that that wind turbine has not stopped spinning since we were here. There is a curve of wind speeds called the Weibull curve, which means, you know, you have 0 miles an hour and you have, you know, roughly 28 miles an hour, which is where most wind turbines, you know, stop producing more. This is where they max out. And it's like, well, how much of the time does it spend in each one of those mile per hour categories? And on land, it's sort of like this. It's like, there's some like calm time. There's a lot of time where it's like there's no wind at all, or it's under 7 miles an hour or so. And you get out onto it offshore, and that curve starts going out this way, where it's like there's almost no time when the wind's not blowing. Right, it's the Weibull curve is pushed out here, so there's always some wind. It may not be a huge amount, but with batteries, having even a small amount of power coming in all the time will extend their lifetime incredibly. But people object to looking at them, so. There's more folks in the back. Back there, and then you. Yeah.
Are batteries getting better?
They're getting better, but they're getting geometrically more expensive as they get better. Like lithium ion is, you know, way better than lead acid, but you know, it's, you know, twice the life and 4 times the cost right now. So it's, you know, it's coming down, but you know, lithium batteries are not a panacea. Anything electrochemical to store electricity is problematic, and lithium batteries have, you know, much better capacity. Their voltage maintains better as they discharge, and so on. Longer lifetime, but they're what you might call a glass cannon. Very powerful, incredibly delicate. Right? You can kill them so much more easily than lead acid batteries. So they all have to have very complex battery management systems on them to prevent you from overcharging them or over discharging them, or, you know, taking power in and out too fast. So lithium batteries, in some senses they're better, in some senses they're more delicate, and they are much more expensive. Now, being out on an island, we might want to consider the fact that there's a certain cost to simply changing out a battery pack. Like, getting that mass of batteries of lead and transferring it to a boat and taking it inland and then, you know, disposing of it. Although you can get money for lead acid batteries or whatever, but you know, there's a cost to that. Whether I believe we're leasing our batteries, but whether you're leasing them or buying them, you know, that cost is built into the lease. Whereas lithium batteries, if they're going to last 4 times as long, they're lighter, it's less weight to ship out here, it's longer time in between those times when you do all that logistical nightmare of getting, you know, the batteries replaced and all that. So sometimes I actually designed a microgrid for an island off the coast of Maine way up north, and did out the numbers on cost per kilowatt hour over, you know, a 20-year period, and found that lithium batteries, even at the price at that time, were slightly better cost per kilowatt hour in and out than lead acid, just because they would stay out on the island longer and there was less, you know, back and forth like that. And they also, because they maintain their voltage, like a lead acid battery, as you discharge it, the voltage drops, and at a certain point the voltage is too low for the inverters to work, right? So that they actually cut off. Whereas a lithium battery the voltage stays where it should be till the very end and drops off. So you effectively get more of the capacity of the batteries being functional. So you can discharge them deeper without damaging them than lead acids. Right now, the lead acids we have, I forgot who told me that, maybe Ron Cordes, Ron told me that under the contract with the lease company, we only discharge them to 75%. Right? We take the first 25% off the top and then charge them back up again. And that will make them last longer, but you're only getting 25% of the capacity of them. If you want to maximize it, you go down to about 50% of charge. Because as your discharges get deeper, the life gets shorter, but you're getting more power out of them per discharge. So there's a place where the lines cross, and that's around 50%. But we're up at 75%, so they're going to last a long time. You know, they're not going to die on us, but still, we're not getting a lot of capacity. Lithium ions, you can discharge them way down without hurting them. As long as you don't discharge them too fast, you can discharge them way down without hurting them, and let them sit there, and then bring them back up. When you discharge a lead acid battery way down and let it sit there, it starts sulfating and dying, and it's anything below 50%, it's dying on you. So with a lead acid bank, you get about 50% of capacity. With if you have a 100 kilowatt hour battery bank, you're really only getting 50 kilowatt hours out of it. With a lithium ion pack, you could get 75, 80 kilowatt hours out of it without hurting it. You know, so there's that. Ron, and then
Yeah, we did a pretty thorough life cycle study of batteries when we were specing the system. Now, this is 5-6 years ago. And we used 24-volt marine lead acid batteries.
Yeah.
And they were the cheapest over the life cycle, including transportation costs, disposal costs, everything else. They were actually far and away the cheapest. And we said, well, we'll come back in 5 years and redo the thing, because if we wanted to switch to lithium ion or nickel cadmium or something, the charge controllers and the inverters could care less.
Right.
The computer, all you have to do is tell it, oh, by the way, that's a nickel, cadmium battery, and it adjusts all its numbers. But as far as I know, we have not redone that life cycle.
Okay. Yeah, because lithium batteries have dropped dramatically in price since then. Yeah. So this gentleman, and then.
Being a family conference, we have a lot of energetic kids on the island.
Yeah.
Is there any way to capture?
No, we're still very, like I was saying earlier in the previous lecture, we're feeble. 10 hours, a human adult, 10 hours on an exercise bike is about 1 kilowatt hour, about 12 cents worth of electricity. We're just feeble. Yeah? You and
When the Paris Climate Accords were here on 2015, I believe, I was teaching a course in this stuff to 300 level students, pretty rational. And the conclusion of everything on how to save the world was the right thing to do and the economical, viable thing to do had to merge.
Yeah,
So that they were the same thing.
yeah,
And the only way that bunch of, it was a project, the only way that bunch of students saw it happening was that everything is electric, everything.
yeah.
Including the electric boats that you guys haven't contracted to bring people out here before, for instance.
Yes, yeah.
And so the question is, this place is a good example of that happening, but probably wouldn't have happened were it not economically viable. Is that correct?
Oh, yeah, we're spending right now, life cycle, about 75 cents a kilowatt hour. At home, you're spending about 20 cents. The system we replaced, that was all fuel oil, was around $2 a kilowatt hour.
Yeah.
So we're not gonna save the world unless we head that way. Is
Yeah.
that fair?
Yeah, it is. And I'll be talking about that on Friday, exactly about costs and real costs and apparent costs and all that kind of stuff. I'm gonna do a deep dive into that, yeah. Back here?
So you talked about how much energy the kitchen takes. How much pollution does it take to grow the food and to get it to Star Island?
Oh, interesting, yeah. Growing food on Star Island versus bringing food onto Star Island. Given the relatively small mass of the food compared to everything else on the Thomas Layton, the people, the water and all that, I don't think we're suffering a big energy penalty from importing food on the island. The saying about like Maine is that you're always 6 inches away from starvation, because that's about how much soil you've got. There's not a huge amount of room out here or a huge amount of soil or a livestock population to do that kind of carbon transfer cycle. So I'd say that we're probably stuck with importing food, and it's not that bad in comparison to everything else that we're doing. That compared to transportation energy and electrical energy, the relative food energy. Actually, most of the food energy is in at the farm and transportation from the farm, and actually transporting it the last 7 miles out here is probably a fairly minimal part of the carbon content of that food. Let's see. You want to ask?
I just have a question about the batteries.
Yeah.
We keep talking about the batteries. What is the recycling of them or disposal of them, and how much energy does that now take to use to deal with that?
Lead acid batteries are one of the most recycled things in America, after aluminum cans. They're about 98% recycled, and basically there's one of those dirty secrets about batteries. Maybe not so dirty secrets, but there's about 5 or 6 or 7 factories in Texas that make all the lead acid batteries in America, essentially, right? Whether you're buying this brand or that brand, from Sears or Walmart or some proprietary thing, it's like 5, 6, 7, I think, factories there, and they say like, how good do you want? They go to the manufacturers and they say, how good do you want them? What quality and how big and what color do you want the case? And they kick them out and they put Sears on Die Hard or whatever, and send them out over here and over there. Then when they're recycled, they go back to Texas. They cut them in half, dump the acid out, crush them, separate the lead, separate the thermoplastic, melt the plastic down for new cases, melt the lead down for new plates, filter the acid, and it all goes back into new batteries. There's about 98%. They lose a little bit in lead oxide and contaminated lead, but it's really the lead acid batteries turn right around and come back out again.
So you're saying like all AA batteries we buy?
Not the AA batteries. The AA batteries that you buy that are non-rechargeable,
Yeah.
they just go in the trash and in the landfill. They are not recycled at all.
Oh.
Lithium ion, you got little lithium batteries, you can take those back to the you know, the hardware store or the electronics store or whatever, and they actually get to try and get the lithium back out of those because it's
So
valuable.
you're talking about the big batteries that they use?
The big, your car battery, things like that, they get sent to Texas.
Okay, I just
Yeah.
wanted to understand which levels of batteries.
If your town is saying, don't put your batteries in the trash, put them in this bucket and come, you know, take them to the town hall,
Yeah.
what are they doing with them?
I assume,
Why go to that effort if you're just gonna throw them away?
well, I think aren't they talking about rechargeable batteries?
No.
No, they're talking about those other ones.
Yeah.
Huh, I didn't know anybody was recycling
I don't
on
know what they're
batteries.
doing with them.
Thrown in the landfill.
Okay, well then,
Oh,
Or your
Probably
town
put it in the
runs
landfill.
trash like ours does, and they do not want that
anyways, other questions here and then there.
Yeah, on the first bell curve that you showed,
Yeah.
there was months, no, time of year at the
Yeah,
bottom.
yeah.
So you're saying that solar array in December or January is not producing much electricity?
Well,
Does it have to do with the cold?
it has to do with the day's shorter, the sun's lower, so the
Oh.
angle of the sun is not as optimum. There's snow on them quite often, and the day is much shorter. You know, the day is like hours shorter. That curve is a little deceptive because the production is restricted by the demand. Like they actually probably would, if there was some other use for it, they actually would produce more than the demand. So the production curve would be higher than it is, but it's restricted by the fact that there's like 2 people on the island, they're not using very much, and so the system throttles itself back and doesn't produce as much because it doesn't need to. So it actually would produce more. But it's generally about 3 to 1. You produce, you know, there's about, in December, you know, you get effectively 2 hours of peak production a day on average, you know, up in this area. And then in June, July, you get 5.5 or 6. So it's pretty much like a 3 to 1 ratio between production in the middle of summer and production in the middle of the winter.
Okay.
And that looks so steep, the curve looks so steep just because there's no usage here, and so that throttles it back. Who else was, yeah, there's 3 here. We'll go in a row. We'll go from left to right, bing, bing, bing.
Okay, not a storage question, but, and I realize there are probably practical limitations that make this impossible, but in theory, the capacity of our septic system, would that generate enough methane to be useful?
That's an interesting question. Generally, when you have human beings who are actually pretty efficient at processing food compared to cows that eat a great deal of bulk, that you have to have an actual municipal sewage system, you know, with like thousands and thousands of people to actually generate enough methane to make it worth it to invest in the equipment to take the methane off, right? You know, the amount of animal manure in this country is just, I did a study years ago about biofuels and also different, you know, biodiesel and ethanol and this and that and the other. And there's also animal manure biodigested into methane. And there was a Senator Kerry, not John Kerry that we all know, but there's another John Kerry from the Midwest somewhere. Yeah, and he commissioned a study and found out that animal agriculture produces about 5,000 cubic feet of manure per American per year. And that's an ugly swimming pool. And if you biodigested all that, you would produce the equivalent of 125 gallons of gasoline per person per year. So there's a lot of energy in that, but that's just because livestock eat grass and, you know, grain, stuff like that, are relatively inefficient, and so there's a lot of material there, but we're not so great. Anyways, next question along.
This is a casual observation, but at night it seems like the generator kind of automatically comes on sundown-ish.
Yeah.
It stays on through the night.
Yeah.
It also doesn't, and this is not a trained diesel here, but it doesn't sound like it's running at a very high load, which oftentimes is not very efficient for an engine once you're running at a load.
True.
So kind of a 2-part question, could the diesel generator cycle on and off as needed, especially with a battery pack that can be charged up and down? And could there be work done to raise the efficiency level of the generator at night?
Now, that's a possibility.
Not much different.
No, that's a possibility in terms of using the top 5% of the battery pack. That you wouldn't deteriorate the battery pack very much if you said we're going to let it go from 100 to 95 and then bring it back to 100 at sort of full blast. The problem is that when a battery pack is nearly fully charged, it doesn't accept charge as fast as when it's fully discharged. So you still wouldn't be running the generator at a super high rate. You have to run it at a low rate for a longer time to get that last 5% in. If you're 75% discharged, the battery bank, then you just like run it full blast and go. But it's tricky to get that last 5% in. It might be a concept to look at what the base load is, and at some point when we're looking at like investing in a new generator, to perhaps get a smaller generator to go alongside the present one that just meets the midnight to 6 a.m. load and can run at full efficiency the midnight to 6 a.m. load, and then use the larger one when there's that demand.
But battery should be at 75% at the time the diesel kicks on.
Right. Yeah. So you're using the top 25%. Yeah. Anyways. Yeah. So that makes it difficult when they're nearly charged. You can't just cram a lot of electricity in them, a lot of power, energy in them all at once. Your question? Yeah.
So why is it that solar panels only have the 2 wires connecting cells, given that maybe it's quite often you have an array with some trees nearby, half the day you might be shaded, but you're losing all that power, and the other half of the day it's not shaded.
The problem is the basis in the silicon electrochemistry is that when you have a solar cell, an electrochemical junction, not electrochemical, a semiconductor junction like that, it only produces about 0.4 of a volt, right? That's the most you can really get out of it. That's just a physical constraint. So you have to stack up those 0.4, 0.8, 1.2 volts, 1.6 volts. You have to stack up a whole bunch of them in series to get a voltage that you can actually use, right? 12 volts or 20 volts or something like that. So there's really no way around doing a series of cells unless you have something that runs on 0.4 volts, which is rare enough. So it's kind of necessary to have that kind of strength. It's just like, you pay close attention to shading and you put modules where they're not going to be shaded. It's just an issue you got to deal with.
How much square footage is the minimum for a panelist? If you want to put them on your house or something, what's the minimum that makes it viable?
That is one of those how big is a rock questions, because it all depends on your finances and your need for return on investment and all sorts of factors like that. But I'll tell you that 15 years ago, people used to put in 2,000 watts on a roof and think, well, that's a big array. But now that modules cost 36 cents a watt, people are putting in 5,000 watts, 6,000, 7,000 watts, and it's all about how much energy you use in a year. You don't want to exceed that, because the power company's not going to pay you for that. Basically, you want to make 99% of your yearly usage, and that's the most efficient size of array. Other questions about star and energy and things like that? Yeah.
This isn't a star specific question, but one thing I was curious about was being able to generate power by taking the sun and focusing it on pipes or something to heat up water and those.
Oh yeah, concentrating solar power, CSP. That is generally a thing for the desert Southwest and really large, megawatt scale generation, because the complexity of the equipment and the need for engineers and technicians to maintain it means there's a certain minimum size that makes sense, and that size is in the megawatts. And it's perfectly viable, and it has a reasonable cost per kilowatt hour at those scales, you know, compared to other methods of generation.
Solar panels.
But what?
How does it compare to solar panels?
At scale, it's fairly similar. Yeah, at scale, it's fairly similar, yeah. But it has to be at scale. Whereas you can make solar efficiently, you know, with photovoltaic panels at, you know, at your house scale or at, you know, tens of thousands of watts or even, you know, hundreds of thousands of watts. You need megawatt scale, millions of watt scale to make CSP viable economically. Yeah.
What's it called?
Concentrated solar power, where they have mirrors, they heat up sodium or, you know, things like that, and they have molten salts of some kind, and they boil water and run turbines and stuff like that. That takes big scale.
And then you have to have a big transmission line.
Yeah, it's the whole bit. One other thing, actually, I hadn't thought of this, and this is probably too expensive, but you know, right now we're doing cogeneration here. Okay, so there's heat exchangers on the generator. So when the generator's running, instead of just blowing the heat out through the radiator like your car does, there's actually some of that heat is being captured and used to preheat water for the kitchen. Brilliant. Way increases the efficiency of your use of fuel. There is such a thing as a boiling water chiller. And that, through the miracle of thermodynamics, takes boiling water in and cools water down. Right? Just like your refrigerator somehow can take heat out of the refrigerator at, you know, 30-some degrees and release it into your room at 70-some degrees. Like that, boiling water chiller takes boiling water off of some source and produces chilled water that can be used for refrigeration. So, in theory, you could take the hot water off the jacket of the engine, run it through a boiling water chiller, produce chilled water for refrigeration, if not freezing, and then take the waste water off of the boiling water chiller and use it to still heat the wash water. So you get tri-generation. You do the cascade there. So the highest use of the fuel, the most sophisticated, is electricity, and then you get chilling, and then you get hot water. And there are some, bottling factories and things like that in California that actually do that. They have like a big, like megawatt scale generator so that they have uninterrupted power, and then they do the chilling, and then they do the wash down water for the bottling line. So I don't know. I don't know if we could, Ron, we could look at this, but I don't think we can get one small enough to really work here. But you know, it's an idea. So it's pushing 11. Any final questions? Anyways, you know, tomorrow we're going to get into the future of renewable technology. So thanks. Appreciate it.